Hello students, welcome back to session 14 of linear transformation class. So in this class we will continue the Hermitian transformations, unitary transformations and normal transformations on finite dimensional inner product spaces. Okay, first I will take up the result. Saying if T belongs to A of V is Hermitian means it is self-adjoint, that is T is equal to T star, then all its characteristic roots are real. Then all its characteristic roots or eigenvalues are real. So for this, so let lambda be an characteristic root of T. Lambda be an characteristic root of T. Then by definition of a characteristic root, there exists a non-zero vector V in V such that T of V is equal to lambda times V. Now you consider lambda into inner product of V and V. So this can be written as inner product of lambda V comma V. So lambda V is T of V comma V, but this can be written as V comma T star of V. Okay, but this, since T is equal to T star, because T is Hermitian, this can be written as V comma T of V itself. So this is equal to V comma T of V is again lambda times V. If we take lambda outside, it comes out with its conjugate lambda bar into inner product of V comma V, means lambda into V comma V is equal to lambda bar into V comma V. This implies lambda minus lambda bar of inner product of V comma V is 0. Now V is non-zero means inner product of V comma V is certainly positive quantity, so it cannot be equal to 0. Therefore the possibility is lambda minus lambda bar is equal to 0 or lambda is equal to lambda bar. Some number, some scalar, if it is equal to its conjugate, means that number must be, or that quantity must be real quantity. So lambda is the eigenvalue or the characteristic root is real. Since lambda is arbitrary, all the characteristic roots of T are real. Therefore if T is Hermitian, then all its characteristic roots are real. Okay. Next, look here. Suppose these are the small results. If S is an element of A of V and if S into S star of V is 0, then S of V itself is 0. S of V itself is 0. So consider inner product of S of V and S of V. So this is equal to S of V into S of V can be written, S can be written as S star whole star. T star whole star is T itself. So this is equal to, if you bring S star here, this comes with S star of S of V comma V. S star of S of V we have assumed to be 0, 0 comma V inner product. So this will equal to 0 itself. Now inner product of S of V comma S of V is 0 implies S of V itself is 0. Okay. Next one, say this lemma says if T belongs to A of V is Hermitian and Tk of V is 0 for every k greater than or equal to 1, then T of V itself is 0. This is an important result. See here, if T belongs to A of V and if Tk of V is 0 for every k greater than or equal to 1, then T of V itself is 0. Okay. Now we choose n such that 2 power of n is greater than k. We choose n such that 2 power of n is greater than k. This is certainly possible. That result you studied in your analysis class. So first we show that T power of 2 power of n, T power of 2 raised to n of V is 0 implies T of V is 0. First we show that T power of 2 power of n of V is 0 implies T of V is 0. So for this what I do is I will take, say S to be, I will take S to be T power of 2 power of n minus 1. Okay, 1 power lesser than the T power of 2 power of n. Now since T is Hermitian, S is also Hermitian. You can verify that. Okay, since T is Hermitian, S is also Hermitian, so that S is same as S star, and S into S star becomes T power of 2n. S into S star becomes T power of 2 power of n. Therefore S into S star of V is T power of 2 power of n of V, but we have assumed that this is to be equal to 0. Now S into S star of V is 0 means just now we have proved S of V itself is 0. S of v itself is 0 means t power of 2 power of n minus 1 of v is 0. Now we assume that S is, if t power of 2 power of n is 0, then we have proved that t power of 2 power of n minus 1 of v is 0. Now you assume that t power of 2 power of n minus 1 is 0, and we can arrive at t power of 2 power of n minus 2 of v is 0, and so on. Finally we get like t power of 2 power of 0 of v is 0, 2 power of 0 is 1 means t power of v is 0. Thus we assume that tk of v is 0, then t power of 2 power of n v is 0 for 2 power of k greater than k, 2 power of n greater than k. Understand now? Now we prove that t power of k of v is 0, then t power of 2 power of n of v is 0 for 2 power of n greater than k, and hence t of v itself is 0, and hence t of v itself is 0. Okay, understand this? Now look here, let's consider the next operator, which is the normal operator. The transformation t belongs to a of v, or the operator t belongs to a of v, is said to be normal operator if t into t star is equal to t star into t. The operator t is said to be normal operator if t into t star is same as t star into t. While unitary operator is t into t star is I is equal to t star into t. That means that operator must be identity operator. It is not compulsory. It only t into t star, t and t star commutes here. Okay. Yes. Note here that if t is Hermitian, then t is normal, because now t is Hermitian implies what? T is equal to t star. Now you multiply throughout by on the left by t. T into t is equal to t into t star. T into t is t square. So t square is equal to t into t star. Similarly, t is equal to t star means multiply on t on right. It becomes t into t is equal to t star into t. So t square is equal to t star into t. So therefore t into t star is t square, which is same as t star into t. Therefore t into t star is same as t star into t. Therefore t is normal. Now unitary operator is also normal. For example, t is unitary implies what? T into t star is equal to I, that's equal to t star into t. Now this implies t into t star is same as t star into t. Therefore t is normal. Means every Hermitian operator and unitary operators are normal operators. Now third one, if n is normal, here simultaneously I use t and n for the operators. Okay. So if n is normal and n of v is 0 for v belongs to v, implies n star of v is also 0. If n of v is 0, then n star of v is also 0. For this, consider inner product of n star of v and n star of v. So this is equal to, I bring this n star to on the left, it becomes n of v. So n of n star of v comma v. So this is equal to n into n star means n star in, this can be written as f of g of x means g of f of x. Accordingly n star into n of v. So but n star into n is same as n into n star of v. So n into n star of v comma v. So this can be written as n star of n of v comma v. So this is equal to n star of n of v is 0. So n of v means 0. N star of 0 comma v. N star of 0 is 0. N star of 0. This is, look here. So 0 comma v, that's equal to 0. Understand now? So this is equal to n star of v comma n star of v is 0 means n star of v is 0. If n of v is 0, n star of v is also 0. Understand this? Okay. Now next one. I am going quickly because these are the very small and easiest results, simple results. Okay. So if n is normal and if lambda is an eigenvalue of n, then lambda bar is an eigenvalue of n star. If n is a normal operator and if lambda is an eigenvalue of n, then lambda bar is an eigenvalue of n star. Okay. Now n is normal implies by definition n into n star is equal to n star into n. First we show that if n is normal, then n minus lambda times I is also normal. For this, you consider n minus lambda I into n minus lambda I whole star. So this is equal to n minus lambda I into n minus lambda I whole star is what? N star minus lambda bar. I star means I itself. So you multiply this n into n star minus n lambda bar into n minus lambda into n star plus lambda into lambda bar into I. So this is equal to n into n star can be written as n star into n because n is normal minus lambda into this I take third term I take into second place. So minus lambda into n star minus lambda bar into n plus lambda into lambda bar into I. So n star you take common, this becomes n star of n minus lambda I minus lambda bar if I take, this is n minus lambda I. So this becomes n star minus lambda bar I into n minus lambda I. N star minus lambda bar I means n minus lambda I whole star into n minus lambda I. Thus we have proved n minus lambda I into n minus lambda I whole star is n minus lambda I whole star into n minus lambda I, so that n minus lambda I is normal. Now they were given lambda is an eigenvalue of n implies there exists a non-zero vector v in V such that n of V is equal to lambda times V. N of V is equal to lambda times V. This implies n of V is equal to lambda times V implies what? N minus lambda I of V is 0. This is singular. N minus lambda I is singular. This implies n minus lambda I whole star of V is also 0 because just now yes, if n of V is 0 then n star of V is also 0. We have proved. So this implies n star minus lambda bar into I of V is 0. This implies what? N star of V is equal to lambda bar of V. This implies lambda bar is an eigenvalue of n star. Means if lambda is an eigenvalue of n, then lambda bar is an eigenvalue of n star. Okay. So this corollary says that one interesting fact that if lambda is a characteristic root of the normal transformation, not only is lambda bar a characteristic root of n star, it doesn't give only lambda bar as a characteristic root of n star, but any characteristic vector of n, any characteristic vector eigenvector of n belonging to lambda is a characteristic vector of n star belonging to lambda bar. Understand this? Any characteristic vector or eigenvector of n belonging to lambda is also a eigenvector of n star belonging to lambda bar and vice versa. Okay, this is to be noted. Okay, now the above result has one important corollary. The corollary says if t is unitary and if lambda is an eigenvalue of t, then lambda bar is mod of lambda is equal to 1, means unitary operators have eigenvalues with modulus value 1 or absolute value 1. Okay, so proof. T is unitary. T is unitary means then it is normal, you know this. And also if lambda is an eigenvalue of t, then lambda bar becomes an eigenvalue of t star. Okay, just now we have shown. Now V can be written as vector, non-zero vector V can be written as I times V because I is the identity operator. So I is means it is normal, it is I is what? Unitary means t into t star. T into t star is I, t into t star of V. So this can be written as t star of t of V. That's equal to t star of t of V is what? Lambda times V. So this lambda can be taken out because t star is a linear operator. So lambda into t star of V. So lambda into t star of V is lambda bar of V because lambda bar is an eigenvalue of t star. So this implies, look here, I of V or V is equal to lambda into lambda bar of V implies lambda into lambda bar is equal to 1 because V is non-zero. This implies lambda into lambda bar means mod lambda square is 1 or mod lambda is 1 or absolute value of lambda is 1, means if t is a unitary operator then eigenvalues of t have absolute value 1. Look here, the normal transformation being both unitary and Hermitian, its characteristic roots are real and have modulus value 1. The normal transformation being unitary and Hermitian, its characteristic roots or eigenvalues are real and of modulus value 1. Okay. Now take up the next result. See here. If n is normal and nk of v is 0, then n of v is 0. Okay, we already proved. If tk of v is 0, then t of v is 0. Now, if n is a normal operator and if nk of v is 0, then n of v is 0. Yes, proof. Let s is equal to n into n star. Then s star is what? N into n star whole star. This is n star whole star into n star, because st whole star is t star in st whole star is t star into s star. So this is got n star whole star into n star. N star whole star is n into n star. N into n star is s itself. So therefore s star is equal to s, implies s is Hermitian. S is Hermitian. Now you consider sk of v. Sk of v is n into n star of k of v. This is n star k into nk of v. N star whole power of k into nk of v is assumed to be 0. So this is 0. So n star k of 0 means it is 0 itself. But just now we have shown if t is Hermitian and tk of v is 0, then t of v is 0. Accordingly here s is Hermitian and sk of v is 0. Therefore by the above result we conclude that s of v is 0. S of v is 0 means what? N into n star of v is 0. N into n star of v is 0 implies n of v itself is 0, because s into s star of v is 0 implies s of v is 0. So accordingly n of v is 0. Thus we have shown if nk of v is 0, then n of v is 0 for the normal operator. Next one, look here. So it has one corollary. So that corollary says, if n is normal and if for lambda belongs to f, n minus lambda I power of k of v is 0, then it implies that n minus lambda is 0, or n minus n of v is equal to lambda times v. If n is normal and if for lambda belongs to f, n minus lambda I power of k of v is 0 means n of v is equal to lambda of v. Again, if n is normal, we already proved that n minus lambda is also normal. So if n minus lambda is normal and n minus lambda I power of k of v is 0 means, according to above result, n of v itself is 0 means n minus lambda I of v is 0, or n of v is equal to lambda times of v. N of v is equal to lambda times of v. Now let us take this result. Let n be a normal transformation, and suppose that lambda and mu are two distinct characteristic roots of n. This is very important. Let n be a normal transformation and suppose lambda and mu are two distinct characteristic roots of n. If v and w are in v and are such that n of v is equal to lambda times of v and n of w is equal to mu times of w, means v and w are eigenvectors corresponding to the eigenvalues lambda and mu. Then these eigenvectors are orthogonal. Means in other words, the eigenspaces formed by these, generated by these eigenvectors are orthogonal. The eigenspaces formed by these two vectors are orthogonal. For this, consider inner product of n of v comma w. This is equal to n of v means lambda is an eigenvalue of v. So n means lambda v comma w. So this is equal to lambda times inner product of v comma w. You call by the number 1. And also given w is the eigenvector corresponding to the eigenvalue mu. Accordingly, n of w is equal to mu into w. This implies n star of w is what? Mu bar into w. Therefore, n of v comma w can be written as v comma n star of w. Okay. So v comma n star of w can be written as mu bar of into w. So mu, if we take mu outside, mu into inner product of v comma w, you call by the number 2. So compare 1 and 2 now. If you compare 1 and 2, you can see that lambda times inner product of v comma w is equal to mu times inner product of v comma w. This implies lambda minus mu times inner product of v comma w is 0. but lambda and mu are distinct eigenvalues. Therefore, lambda minus mu cannot be 0. Therefore, the possibility is inner product of v comma w is 0. If inner product of v comma w is 0 implies the vectors, eigenvectors v and w are orthogonal. V and w are orthogonal. They are orthogonal means the spaces generated by v and w definitely mutually orthogonal to each other. Okay. Next one. Look here. If n is a normal transformation, on V, then there exists an orthonormal. If n is a normal transformation on V, then there exists an orthonormal basis consisting of eigenvectors of n, in which the matrix of n is diagonal. This is a very important result. Okay. If n is a normal transformation on V, then there exists an orthonormal basis. Consisting of eigenvectors of n, in which the matrix of n is diagonal. Okay. So now look here. Since V is a inner product space over the complex field, here in this section we assume that it is F is a complex field. So since V is a inner product space over the complex field, the minimal polynomial of n has all its roots in where? In C only. Okay. The minimal polynomial of T has, or here n, the minimal polynomial of n has all its roots in C, and hence n has distinct eigenvalues, say lambda 1, lambda 2, etc. lambda n are all in C. Okay. Then n has all its distinct eigenvalues, say lambda 1, lambda 2, etc. lambda k are all in C. But if all the eigenvalues lies in C, then we already studied the theorems based on this. So accordingly, we can decompose V as the direct sum of V is equal to V1 plus V2 etc. up to Vk, where each Vi contains set of all V belongs to V such that n minus lambda I power of ni of V is 0. N minus lambda I power of ni of V is 0 means each Vi belongs to Vi. Each Vi belongs to Vi is annihilated by which transformation? N minus lambda I power of ni. This is not T, this is n. N minus lambda I power of n annihilated by. Okay. So we know that if n is normal and if for lambda belongs to F, n minus lambda power of k of V is 0 implies n of V is equal to lambda times of V. Okay. Just now we have proved this result. According to this, what will happen here by the above result? It implies that Vi consists only of n minus lambda power of ni of V is 0 means what? N of V is equal to lambda I times of V. N of V is equal to lambda I times of V means lambda I becomes the eigenvalues, means each of these spaces contains eigenvalues. Each of these spaces contains eigenvalues with the corresponding eigenvector. Okay. Just in the above result we have shown that the eigenvectors are mutually orthogonal. Okay. So look here, and the inner product by the above result Vi consists of only of eigenvectors of n belong to the eigenvalue lambda I. Okay, understand this? And the inner product on V induces inner product on each subspace Vi. Okay, definitely in the inner product on V definitely induces the inner product on these subspaces. And since a very finite dimensional inner product space has an orthonormal set as a basis, okay, we can find an orthonormal basis for each Vi. This is already you have studied in your inner product space class. That means a very finite dimensional inner product space has an orthonormal basis that we have proved using Gram-Schmidt orthogonalization process. Now here the elements lying in distinct Vi's are orthogonal. Just now we have proved, and the elements lying in distinct Vi's means these are the eigenspaces. Okay, eigenspaces means they are orthogonal. So under elements lying in distinct Vi's are orthogonal. Thus putting together all the orthonormal bases of Vi's, we obtain an orthonormal basis of V. that also we have studied. So if V is the direct sum of V1 and V2, then the basis of V1 and V2 constitute the basis of V. Here V being splitted as k number of subspaces. So all the orthonormal basis, if we combined, then that orthonormal basis becomes the orthonormal basis for the vector space V. Okay. So in this orthonormal basis, definitely it contains eigenvectors because each Vi contains eigenvectors. Therefore, if the eigenvalues lies in a field, then by the triangular canonical form, yes, we can declare that hence in this basis the matrix of n is diagonal. Okay, in this basis the matrix of n is diagonal. Okay, so that's the last thing is very important result. So next I will take up the another important result. So here, look here, we are saying that in this theorem the normal transformation n is Hermitian if and only if its characteristic roots are real. The normal transformation n is Hermitian if and only if its characteristic roots are real, and is unitary if and only if its characteristic roots are all of absolute value 1 or modulus value 1. Okay, so let us prove one by one. Okay, first suppose the normal transformation n is Hermitian. The normal transformation n is Hermitian implies what? N is equal to n star. N is equal to n star. Now let lambda be an eigenvalue of n. If lambda is an eigenvalue of n, then there exists a non-zero vector v in V such that n of V is lambda times of V. Now we consider lambda times of inner product of V comma V. This already proved. Okay, lambda times of inner product of V comma V is lambda of V comma V under inner product. So this is equal to lambda of V means n of V comma V. So this can be written as V comma n star of V. So V comma n star of V is same as n because n is Hermitian. Okay, n of V. So this is equal to V comma lambda of V. So this is equal to lambda bar into V comma V. This implies lambda minus lambda bar of inner product of V comma V is 0, because V cannot be 0 means inner product of V comma V cannot be 0. Therefore the possibility is lambda minus lambda bar is equal to 0 or lambda is equal to lambda bar. If lambda is equal to lambda bar, then we can declare that lambda is real. So we have assumed that T is the transformation is n is Hermitian, and we have proved that the eigenvalues are real. Conversely, let n be the normal transformation and has only real eigenvalues or real characteristic roots. We showed it is Hermitian. Now if this happens, then definitely for some unitary matrix U, UN U inverse is same as UN U star. UN U inverse is same as UN U star. That becomes a diagonal matrix. UN is equal to UN U star is equal to D, where D is the diagonal matrix with entries on the main diagonal, with real entries on the main diagonal. So then what will happen? Then if it is a diagonal matrix with real entries on the main diagonal means then D is equal to its adjoint. So D becomes D star. So this implies D is UN U star whole star is equal to UN U star. Okay. So this implies UN star U star is equal to UN U star. That D star I taken first. Okay. That's up. D star, value of D star taken first and D second. Okay. So this implies UN star U star is equal to UN U star. So since U is invertible, so multiply this gives N star is equal to N. Now N star is equal to N means what? N is a Hermitian transformation. Okay. So we have assumed that it has only real eigenvalues and we have shown that N is Hermitian. Second result. Now let the normal transformation N be unitary. The normal transformation N be unitary. We will show that the eigenvalues of N are of absolute value or modulus value 1. So let lambda be an eigenvalue of N, which is arbitrary. Then lambda bar definitely is an eigenvalue of N star. Okay. Now you consider V, the vector V. V can be written as I into V. I into V is N is unitary means n into n star of v, n star is equal to I. So I can return it as n into n star of v. This is equal to n star of n of v. So n star of n of v is what? Lambda times of v. Since n star is linear, this can be written as lambda times into n star of v. Lambda into n star of v can be written as lambda bar into v. Thus we have lambda into lambda bar is equal to 1. Since v cannot be 0, or mod lambda square is equal to 1, or mod lambda is 1, means the eigenvalues are of absolute value 1. Here, since lambda is arbitrary, all the eigenvalues of n are of absolute value 1. Now converse part let us consider. This is a very important part. So conversely, suppose n is normal and has only eigenvalues of absolute value 1. Then what will happen? Then for some unitary matrix u, un u star is same as un u star, that is D, where D is the diagonal matrix. Where D is the diagonal matrix containing the eigenvalues on the main diagonal. Say for this, say let D be contains lambda 1, lambda 2, etc. lambda n on the main diagonal, eigenvalues on the main diagonal. Then D star becomes lambda 1 bar, lambda 2 bar, etc. lambda n bar. So consider D into D star. D into D star becomes lambda into lambda 1 bar, lambda 2 into lambda 2 bar, etc. lambda into lambda n bar on the main diagonal. Elsewhere it is 0. So this is equal to what? Lambda into lambda 1 bar means mod lambda 1 square, but mod lambda 1 square is each, we have assumed that each lambda 1 has absolute value 1. So accordingly this is 1, means this is equal to I. So what will happen? D into D star is I. Now un u star is D, un whole star is D star. So this is u star whole star means un star u star is equal to D star. Therefore D into D star is equal to un u star into un star u star. D into D star just now we have shown to be I. So I is equal to un. I will combine these two terms, un u star u, n star u star. So un u star u is, look here, un u star u is I. Okay, u is a unitary operator, so n star into u star. So this is equal to, this implies multiply on the left by u star, right on the u, this becomes u star into un n star u star u. So u star into u again I, this is equal to u star into u is I, u star into u is I, therefore only remaining is n into n star. Therefore n into n star is equal to I, meaning n is unitary. So we have assumed that the normal transformation n has all its eigenvalues have absolute value 1, and we have shown that n is a unitary operator. Okay. So thus if the normal transformation n is Hermitian, then all its eigenvalues are real and is unitary if and only if all its eigenvalues are of absolute value 1. Okay. Next you consider this result. Let n is normal and n into a is equal to a into n. N into a is equal to a into n. Then a into n star is same as n star into a. If n is normal operator and if for some operator a into n is same as n into a, then a into n star is same as n star into a. For this, let x be, you denote x be a into n star minus n star into a. Let x be a into n star minus n star into a. Now we show that x itself is 0. We show x is 0 means what will happen? A into n star is equal to n star into a. Now to show x is 0, it is equivalent to showing that trace of x into x star is 0. To show x is 0, it is equivalent to show that trace of x into x star is 0. Why? Because look here, if a is any linear transformation on V, then trace of a into a star can be computed by using the matrix representation of a in any basis of V. Definitely we can do this. We pick an orthonormal basis of V. In this basis, if the matrix of A is alpha ij, then matrix of A star is what? Beta ij, where beta ij is what? Alpha ji bar. This we already discussed. Okay. Therefore, look here, trace of A into A star becomes, trace of A into A star means summation I summation over ij. Alpha ij into alpha ji bar means what? Mod of alpha ij whole square. Therefore, trace of A into A star is 0 implies each of these alpha ij's must be 0. If each of these alpha ij's must be 0 means A must be 0. Therefore, trace of A into A star is 0 happens if and only if A is 0. Understand now? So, trace of A into A star is 0 if and only if A is 0. So, that's why we are going to show that x is 0. It is equivalent to showing that trace of x into x star is 0. Trace of x into x star is 0. Now, you consider x into x star. X is what? A into n star minus n star into A. X star, you take a adjoint of this, A into n star minus n star into A whole star. So, this becomes A into n star minus n star into A. This whole star means this becomes n into A star minus A into n star, A star into n. So, this is equal to A into n star minus n star into A. I will multiply with n into A star first, and next is minus A into n star minus n star into A into the multiplication to the second term, A star into n. Now, look here, they were given n commutes with A, n commutes with A and n commutes with A, as well as n is normal means n into n star is equal to n star into n means both n commutes with both A and as well as n star. N commutes with A as well as n star. Therefore, the above term becomes x into x star is equal to n times A into n star minus n star into A star minus A into n star minus n star into A star into n. So, you call this by the term B. So, this becomes nb minus B into n, where B is what? A into n star minus n star into A star. Okay. So, therefore, trace of x into x star is what? Trace of nb minus bn. But trace of nb minus bn you found to be 0. This is always 0 because trace of ab is same as trace of ba, means trace of x into x star is 0. Trace of x into x star is 0 means what you can declare? X itself is 0. X itself is 0 means x itself is 0 means A into n star is same as n star into A. Thus, we have proved if A into n is equal to n into A, then A into n star is same as n star into A. Next result, you consider the linear transformation T is Hermitian. The linear transformation T is Hermitian if and only if inner product of TV comma V is real. TV comma V is real for all V belongs to V. Okay. Now, look here, T is Hermitian implies what? T is equal to T star. Now, we consider the inner product of TV comma V. So, this is equal to inner product of V comma. So, we transform T to here means T star of V. So, this is equal to V comma T star means T. So, T of V. So, this can be written as x comma y bar means y comma x means T of V comma V bar conjugate. Now, T of V comma V is equal to T of V comma V conjugate implies T of V comma V is real. T of V comma V is real. Conversely, you assume that T of V comma V is real for all V belongs to V. Then what will happen? Inner product of TV comma V is equal to inner product of TV comma V bar. This is equal to V comma T of V. So, this is equal to V comma T can be written as T star whole star of V. So, T star, if you transform this to here, it becomes T star of V comma V. So, we see that T of V comma V is T star of V comma V implies you transform this term to on the left, it becomes T of V minus T star of V comma V is 0, or this implies T minus T star of V is comma V is 0. This implies V cannot be 0 means T minus T star is 0 or T is equal to T star. T is equal to T star means T is Hermitian. Okay. So, we have proved that the transformation T is Hermitian if and only if inner product of tv comma v is real for all v belongs to v. Okay. Next one, look here. The Hermitian linear transformation is non-negative if and only if all its eigenvalues are non-negative. The Hermitian linear transformation is non-negative if and only if all its eigenvalues are non-negative. So suppose T is Hermitian and is non-negative, means T is greater than or equal to 0. So we have to show all its eigenvalues are non-negative. Let lambda be an eigenvalue of T. If lambda is an eigenvalue of T, then by definition there exists a non-zero vector V belongs to V such that T of V is equal to lambda times of B, or in other words V is the eigenvector. Then we know from inner product that inner product of T of V comma V is always non-negative, but this is equal to T of V is lambda V comma V, this is lambda into V comma V. This implies lambda into inner product of V comma V is greater than or equal to 0. But V is non-zero means inner product of V comma V is positive. Inner product of V comma V is positive and the total term is non-negative, means lambda should be non-negative. Since lambda is an arbitrary value, all its eigenvalues are non-negative. Conversely, suppose T is Hermitian. And all its eigenvalues are non-negative. We have to show T is non-negative. Okay. Let V1, V2, etc. Vn be the orthonormal basis of V consisting of eigenvectors of T. Okay. So let V1, V2, etc. Vn be the orthonormal basis of the vector space, inner product space V consisting of eigenvectors of T. This already we have proved in the inner product space. The orthonormal basis consists eigenvectors. Okay. Then any vector V in V can be written as linear combination of basis elements. So therefore V can be written as alpha 1 V1, alpha 2 V2, etc. alpha n Vn. Now you consider the inner product of T of V comma V. So T of V is again alpha 1 V1, alpha 2 V2, etc. alpha n Vn, comma inner product of alpha 1 V1, alpha 2 V2, etc. alpha n Vn. So you expand this, it gives first one. Look here. Since T is linear operator, it becomes alpha 1 into T of V1 plus alpha 2 into T of V2, etc. alpha n into T of Vn. Now alpha 1 into T of V1 is what? Lambda 1 V1. So I written alpha 1 into lambda 1 V1, alpha 2 into lambda 2 V2, etc. alpha n into lambda n Vn, comma the other terms you write as it is, alpha 1 V1 plus alpha 2 V2, etc. alpha n Vn. Now you expand this inner product. Now it gives alpha 1 into, look here, first term is alpha 1 bar into lambda 1 into inner product of V1 comma V1. So all other combinations get zeros because inner product of V1 comma V2 becomes 0 because these are orthonormal vectors. So this is equal to alpha 1 into lambda 1 into alpha 1 bar into V1 comma V1 plus alpha 2 into lambda 2 into alpha 2 bar into inner product of V2 comma V2 and so on, alpha n into lambda n into alpha n bar into inner product of Vn comma Vn. This can be written as mod of alpha 1 square into lambda 1 into inner product of V1 comma V1 plus mod alpha 2 square into lambda 2 into V2 comma V2 under inner product, etc. mod alpha n square into lambda n into inner product of Vn comma Vn. Okay. So this is T of V comma V. Now look here. Each lambda is non-negative. We have assumed that all its eigenvalues are non-negative. Converse part we have assumed, and mod of alpha I square is always positive quantity. Under mod means it is always positive quantity. Therefore the right hand side term becomes, this term becomes non-negative. Right hand side term becomes non-negative means, so left hand term also becomes non-negative means inner product of TV comma V is greater than or equal to 0 for every V belongs to V. If inner product of tv comma v is greater than or equal to 0 for every vector in v, means t itself is a non-negative operator. Okay, t itself is a non-negative operator. We have assumed that the eigenvalues of t are non-negative, and we have shown that t itself is non-negative. Okay, this is also an important result. So finally I will give this result. Say if T is Q Hermitian, then all its eigenvalues are pure imaginary. We have already proved if T is Hermitian, then all its eigenvalues are real. Now I am showing that if T is Q Hermitian, then all its eigenvalues are pure imaginary. So for this, let lambda b is equal to a plus ib be an eigenvalue of T, where a and b are real. Okay. Then this is an eigenvalue, means there exists a non-zero vector v in V such that T of V is equal to lambda times of V. Now you consider lambda into inner product of V comma V. Lambda into inner product of V comma V is equal to what? Inner product of lambda V comma V. So lambda V means T of V comma V. So this is equal to inner product of V comma T star of V. So this is equal to inner product of V comma T star is same as, since T is Q Hermitian, T star is equal to minus T. So minus T of V. So this is equal to minus inner product of V comma T of V is lambda times of V, therefore minus lambda times of V. You take lambda outside, it becomes minus lambda bar into inner product of V comma V. Now left is lambda into V comma V, right is minus lambda bar into V comma V. You transform this term to the left, it becomes lambda plus lambda bar into inner product of V comma V is 0. But V is a non-zero vector, so the inner product is positive or it is non-zero. Therefore, the only possibility is lambda plus lambda bar must be 0. Lambda is what? A plus ib. Lambda bar is what? A minus ib. If you sum up, you see that 2 times a is 0. 2 times a is 0 means a itself is 0. A itself is 0 means in the lambda, if a is 0, you get I into b. I into b means which is a pure imaginary part. Okay, the eigenvalues is pure imaginary. Thus, we have shown that if T is a skew Hermitian operator, then all its eigenvalues are pure imaginary. Okay, these are the few results for this class, and I will continue in the next class. Okay, thank you very much for listening.